Well, we've spent most of the course hunting for derivatives of functions and then using those derivatives to solve problems. The remainder of this course is going to be focused on what we call integration. And as it turns out, there's a relationship between derivatives and integrals. So lesson 6.1, we're going to introduce the idea of an antiderivative and an indefinite integral. And we'll learn some techniques for finding those functions. So let's start with a definition. A function capital F is an antiderivative of f on an interval I if the derivative of capital F, f prime, is equal to f of x for all x in the interval I. So this big capital F, if you take the derivative of it, you end up with function f of x. And it turns out that the function f of x has an infinite number of antiderivatives, all of which vary by a constant. So think about this function, 3x squared plus 2x. This would be considered f of x. One antiderivative, capital F of x, would be x cubed plus x squared plus 153. If I take the derivative of this function, I'd get 3x squared plus 2x plus 0, which is our f of x. But wait a minute, take a look at this capital F. X cubed plus x squared minus 17. You take the derivative of that, you still get f of x because it's 3x squared plus 2x plus 0. Same thing down here with this third f of x, capital F. I take the derivative of this, 3x squared plus 2x, still get f. All of these are possible antiderivatives of the function 3x squared plus 2x. And you'll notice the only difference is they have a different constant added on the end. As it turns out, it doesn't matter which constant there. When you take the derivative, it becomes 0 anyway. So all of these antiderivatives for this particular function f of x are going to differ by a constant. So this is where the letter capital C comes in. Since all the antiderivatives of a function f differ by a constant, we're going to use capital C to represent that constant. So for our good friend 3x squared plus 2x, we would say that the antiderivative of 3x squared plus 2x would have this form. Capital F of x would be x cubed plus x squared plus c. This constant here will hold the place for any of those constants that we could have there. It can actually be any value, because no matter what the value of c is, when you take the derivative of f, of capital F, you're going to end up with 3x squared plus 2x. So anything that looks like this with some number at the end, x cubed plus 3x squared plus capital C, the derivative of that is always 3x squared plus 2x. So this idea of antiderivatives has a whole notation and language surrounding it. And that's what I want to introduce now. We're going to talk about integrals. So the process of finding all the antiderivatives of a function, that's called antidifferentiation. But more often than not, you're going to hear it referred to as integration. Antidifferentiation and integration mean the same process. And as I mentioned, there's a special notation to indicate that integration is going to be performed. And the notation looks like this. If you want to find the antiderivative of a function lowercase f, then you would use this notation. It's a curvy, elongated S-type shape, which we call an integration symbol. Then you put the function which you're looking for the antiderivative of. And at the end, you put the variable, which is your variable of integration. You put a little dx at the end, that differential. When you write this notation here, that's the same as finding the antiderivative, and remember they all differ by a constant. So this special notation here is the integral sign, the function that you want to find the antiderivative of, and the variable with which we're finding the integration with respect to. Now most of this section is concerned with techniques or rules which make it easier for us to find these indefinite integrals, these general antiderivatives. And so I'm going to run through a bunch of the rules that were discussed in the chapter, in the section, and then show you some examples of how we use those rules. So the first rule is called the constant multiple rule. And basically what we're saying is if we're finding the integral or the antiderivative of some constant, remember this is the symbol that says we're going to find the integral or the antiderivative. This is our variable with which we're finding the derivative with respect, the antiderivative with respect to. If this k is our function, then the antiderivative is going to be k times x plus c. This x magically appears. Okay, and the reason is because when you take the derivative of this thing, you end up with this thing, k. All right. Let me show you that in action. So let's consider the integral of the function 5, integral of 5 dx. Our rule says that we're looking for a constant, k, so our k is 5, that the antiderivative of that thing is going to be k times x plus c, right? And so I think this is the indefinite integral, 5x plus c. And the way you check that is this. What's the derivative of 5x plus c? If capital F of x is 5x plus c, the derivative, which we would call capital F prime of x, is going to be 5 plus 0, which is 5, and that's what we wanted, see, the 5 right there. So this is our antiderivative, general antiderivative, 5x plus c. There's a power rule for antiderivatives just like there is a power rule for derivatives. And basically this is just the reverse of that process that we had for differentiation. So if we end up with a function x to the n and we want to find out what it was right before we took the derivative, that's what antidifferentiation really is. The way you figure that out is you add 1 to the exponent, right, instead of subtracting it away. But to account for the fact that that n plus 1 is going to come down in front, and we want to end up with a 1 there, we're going to divide by n plus 1 also, or in this case multiply by 1 over n plus 1. So the power rule is if you're integrating x to the n, the antiderivative is 1 over n plus 1 times x to the n plus 1 plus c. Don't forget the plus c. Number one thing people forget when they're working on these problems is the plus c. And that's because when you take the derivative of this, it doesn't matter what number's there, that constant goes to 0. Let's look at an example of this one. So let's consider the function x cubed. We're going to do the integral of x cubed. And our rule said that we're going to add 1 to n. And remember, this right here is n, so n equals 3. And we're going to make this 1 over 3 plus 1, which is 4, x to the 3 plus 1, and then plus c. And so what this works out to be is 1/4 x to the 4th plus c. You may also see it written as x to the 4th over 4 plus c. And again, like in our last example, if you take the derivative of this thing, the 4 comes down, right? And it'd be 1/4 times 4 x cubed plus 0, and then this turns into a 1, so we do end up with x cubed, which is what we wanted at the beginning. So the integral or the general antiderivative of x cubed is x to the 4th over 4 plus c. With integration, we do have a constant multiple rule, just like we had with derivatives and limits. And basically it says if you have some function that's multiplied by a constant, and you want to do the antiderivative or the integral, you can simply factor that constant out and then do the antiderivative on the function and multiply it back on. So let me show you how that looks in practice. So here we have the function 10x to the fourth, and as you can see, this is just x to the fourth multiplied by some constant 10, which we're going to call k. And the rules of integration say that you can factor that 10 out and just do the integral on x to the fourth, which is good because I just got done showing you how to do x to the fourth. So this would look like this. We'd have 10 times 1 over n plus 1, so this would be 1 over 5, x to the fifth plus c. Okay. Now, remember the reason I was able to do that is because n was 4 here. Now we're going to distribute this 10, but I don't want you to be surprised when I don't write 10c. I just write c again. So 10 times 1/5 is 2. So this would be 2x to the fifth. 10 times some constant is some other constant. So usually what we do is we write c again. But keep in mind, this c is not the same as this c. We'll call this c1 and this c2. But the bottom line is that the antiderivative will have the form 2x plus 2x to the fifth plus c. Just like limits and derivatives, we do have sum and difference rules, right? And all it says is if you're integrating the sum of two functions, you can do each integral separately and then either add or subtract them. Very similar to limit rules and derivative rules that we studied earlier in the year. So here's an example of a function that's made up of adding two functions, right? We have a sum. So the sum rule basically says we can do this integral, the integral of x squared dx, plus the integral of 2x dx, and then when we're done we can just add those two functions together to make our antiderivative. Now I do want to show you one thing. I'm going to rewrite this again, and I'm going to factor that constant multiple out, that 2. Okay, so now this just simply becomes two power rules. Here n is 2, and here n is 1. So the antiderivative on the left here will be 1/3 x cubed plus some c, which I'll call c1, plus 2 times 1/2 x squared plus some c, which I'll call c2. And what we'll do is we'll distribute this 2, right? And we'll put all the constants together in one big C. So this whole antiderivative, I should put some equal signs here, is 1/3 x cubed plus 2 times 1/2 is 1, so this is just going to be x squared. And then I've got my c1 plus my 2c2, and that's going to be some other constant, so we'll just call it a big C. So our solution here for the value of this integral is 1/3 x cubed plus x squared plus c. And as you get experience with these, you probably won't do all this writing. What you'll do is simply look at it and say, oh yeah, I can do x squared, oh yeah, I can do 2x, and I'm just going to put one big C on the end. That's kind of the point of the sum rule. So remember everybody's favorite function, e to the x? E to the x was cool because the derivative of e to the x was also e to the x. And that means that the antiderivative is also going to be e to the x, except that we have to account for that constant. So these antiderivatives are going to be relatively straightforward. Let's consider the function 2e to the x. So we want to find the integral or the antiderivative of 2e to the x. Well, the first thing I'm going to do is invoke my constant multiple rule, factor that 2 out, and then we just learned that the integral of e to the x dx is e to the x plus the constant c, and then I distribute the 2, I get a whole new constant 2c, but I'm going to call it some other c. And by the way, it's not just me that takes this c, multiplies it by 2, and comes up with this c. That's the standard practice for these antiderivatives. Basically, anything that you learn from me is pretty much something that I learned from somebody else, and that whoever I learned it from learned it from somebody else. You know how this works. The point here is that finding the derivative, or the antiderivative, for functions that involve e to the x is fairly straightforward. The last rule that I want to take a look at is what we're going to call the 1 over x rule. We learned in our sections on derivatives that the derivative of the natural log of x was 1 over x. But there was a catch, that the derivative of the natural log of negative x was also 1 over x. So when we're going backwards, we're not sure which one it was. We're not sure if this started out to be x or negative x. So to account for that, we simply throw the absolute value bars in there. But the point is now that if we have the function 1 over x, that we can write down the antiderivative function. Let's see that one in action. So here we go. We're going to try to do the antiderivative, or the integral, of 4 over x dx. Now I just got done telling you that the integral for 1 over x has a formula. But what about 4 over x? Well, this 4 is just a constant multiple. I can factor it out, and then I will be left with a 1 over x, which is what we just learned. And so the solution on this problem is going to be 4 times the natural log of the absolute value of x plus c, and then you know my whole trick with the constants. I'm going to distribute the 4, I'm going to multiply c by 4, but I'm still going to call it c because it's some other constant. Like I said, that's a standard trick. So hopefully this has been a helpful introduction to lesson 6.1. I went over many of the integration rules and showed some examples so that you kind of get the ball rolling here. Of course, you know you can contact me if you have questions. Good luck.